Let's see. Now what we want to look at is a microscopic impulse. All right, microscopic impulse. So how are we doing on? Oh, that's the first half. Okay. So this is really about microscopic impulses, the detailed force versus time, right? In reality, we don't really always just have a constant force. You know, if an avalanche hit you in the back while you're on a snowboard, is that going to give you a constant force? Probably not. Okay. Oh shit. This is the departmental. That tastes like William Marsh Rice right there. I think that might be his original breath in this thing. This is the departmental beach ball. Okay? And it's got a few vectors on it from some inferior teaching that was done before today. But I'm going to use it to demonstrate this momentum concept. So we're going to give this an impulse, right? So when you hang something like this, it's a way to make it weightless in a sense. If we want to see how does this move in 1D without any interference, just under its own sort of, inertia, see, it's mostly 1D free here. If you get far enough over, then of course it pulls it back. So anyway, here we go. So there it is. So we're going to shoot it with the big gun, and we're going to apply an impulse to it with the bullet. I meant to come practice this last night, and I didn't. So this is the first time I've ever shot that with this bullet, so it might fly off and hit you guys. So I was going to practice it and see if it hits you guys, so just look out. Watch your face. Can you also use P equals ma delta t to solve for acceleration, then for velocity too? Probably not, because we're doing something else. We'll get to it. Okay, so let's see. Watch if we apply impulse, does it move? You've got to be kidding me. Oh, there may be aerodynamic problems, and it may be impossible to hit it, because it may feel the... Let's find out. It may go around it every time. I didn't think of that. Wow. I really should have done this ahead of time. Wow. We're seeing aerodynamics at work. Check this out. There we go. Oh my God, I'm sorry. Okay, I didn't think it would fly off that fast. Okay. You saw it go, right? We won't do that again. Sorry. You're okay? Okay, you're okay. Wow. If that had hit you in the face, I would really be worried. I'd really be concerned. Okay, let's take this down now. We set that up ahead of time, right? See, that wasn't an accident. Okay, so what we had here is we had a beach ball like this, right? And we had a bullet like this, right? So this had initial P1 initial, and this had initial momentum of P2 initial, which was 0. They were just sitting still. This was going like that, right? So it's got its vector. This is just sitting here like this. And of course, after they hit, we're going to pretend it remained in one dimension as it was supposed to. And this kind of came to the side, and suddenly this had P2 final, and the bullet bounced back like that. So we had P1 final. So the situation looks something like that. Before and after. Almost like an energy problem in this case. Okay, so let's make a plot of what the force versus time probably looked like. And the reason I have all these soft things out is you can imagine when the bullet hit, it didn't apply a constant force, right? It went in, and the things like a spring and the bullet is elastic, like we talked about, like a spring. So at first the force is very small, and then it gets really big, and then it flies out again. So it's really not a constant force. It's like a peak force. It looks something like this. That's what really happens when two things crash into each other, is things deform, they act like springs, and you get some shape like that. So if we were going to do this, we would say, oh my God, we have to do an integral from T1 to T2. This is T1, T2, of whatever that function is, right? This is f as a function of t. I'll go ahead and put a function of t. Don't think they're multiplied. Of that function of time times dt, right? And that would give us the impulse. But we know that's actually the area under the curve. is our sort of a geometrical interpretation of that, right? So what we do then in problems to make them doable is we say, no, let's just think about the average force, right? Force is a function of time. We say this has some area under the curve. So let's do a lower area, but constant and for longer, like this, between T1 and T2. Right? Where this is the F average. Right? So then we can say J equals F average times delta T. T1 minus T2. And then it's constant. And it makes it easy, right? So what you do is you pick, or you set, pick, if you're choosing set, if you're writing a problem, F average to make the areas equal. That's the idea, is if we bring this down, if we were to put F average up here, then clearly the area under the square would be bigger than the area under the peak. But if we start lowering the height, then eventually the area of the rectangle will equal the area of the peak. Okay? So there is some value of F average that you could set here that allows you to make this approximation. Okay? So in every problem we'll have you do, it's just going to be F average. Okay? I don't think, well, who knows? I don't want to make any crazy broad statements, but you never know. But most of the time, we're just going to make you do F average. All right? And one question that we'll deal with more on Thursday that you might wonder about here is, wait, which force is which? Are we talking about the force that the bullet applies to the ball or the force the ball applies to the bullet? So I'm not even going to write it down at this point, but remember, that's an action-reaction pair, so they're the same. Okay, their directions are different, but if this is just the magnitude of F, the same area, the same impulse is being applied to this that's being applied to that. It's just here the impulse is forward, here the impulse is backwards. That's the only difference. Okay, but that'll be important when we do conservation next time. Okay? All right. Let's read this and just take it easy. Same integral to find the average value of F as you would to take the... So here's a couple questions. Why don't we do these rather than jump in, because we only have like 2 minutes and then we'll take a break. So here's two good questions. Let me see if I can figure out what they're saying. Excellent questions. I just don't understand. Let's see. Shoot. Oh my God. Don't you need the same integral to find the average value of F as you would to take the integral of F over the interval? Yeah, so the point is, if you get this F average, you don't have to do an integral. Oh, and also remember, this isn't a function anymore. So F average is a constant. So the advantage of having F average is simply that it's just a constant times delta T. So there's no integrating to do or anything. What's special is it's equal to the value that makes these equal. Okay? So it's always less than the peak F. So in problems, they'll just say, find F average. A way we can make this tricky is, do you think the peak force is larger than F average or less than F average? It's larger, right? Because that's the way F average works. Let's answer this one. Excuse me, this came in earlier. Can you also use P equals ma delta T to solve for acceleration, then for velocity too? If this were the first 6 weeks, you could, yes. Right, so we can always tie this back to kinematics and do things by kinematics, but we're trying to show this new way of doing things with momentum, conservation momentum. Okay.